Okay, in this set of guide sheets, we're going to figure out how to deal with situations where the forces don't naturally line up but are at some kind of angles with each other. We're going to go back to our concepts of vectors, and we're going to break down some components and line everything up so that they do naturally fit together, and then go ahead and cancel them out and figure out what the leftover force is. So for information, again, this URL would be a place to go to look if you're having questions about how to do any of these parts. We're looking at situations of translational equilibrium as possibilities. That's when all the forces add up to 0. If the object is moving, it will move at constant speed in a straight line. If the object is stationary, then if all the forces add up to 0, then we'll have static equilibrium. The object will stay at rest. Now, if those two conditions are not met, if we have a net force, some kind of leftover force, then the object will undergo acceleration. So we're going to look at all that, and we're going to be applying the second law of motion, called the law of acceleration. When you add all the forces on an object, the net force is equal to the mass of that object multiplied by its acceleration. Okay, so in this first one, we have 3 forces acting. First thing is I'm going to calculate the mass. Mass is equal to the weight of the object divided by the local gravitational field strength, little g. For this case, I'm going to use g as 9.8 newtons per kilogram. Since 19.6 is 2 times 9.8, that would tell us that we have a mass of 2 kilograms for both of these objects. They both have the same weight. Now I want to do essentially apply F equals ma, and the thing I'm asked for is what is the acceleration value. So I'm going to solve that for acceleration. It's the net force divided by the mass. Now in our first case, these two cancel out directly. We have 12 newtons as our overall leftover force. So 12 newtons divided by 2 kilograms equals 6 meters per second, and that is going to be to the right. The acceleration will be directly proportional to the net force, which means it will be exactly the same direction. The only difference with our second one over here, the mass is still 2 kilograms. It's the same object, or at least the same type of object, but now we not only have an applied force, we also have a frictional force. So when I look for the acceleration and I go to do this summation of forces, I'm going to call this positive and this side negative. So any force to the right is positive, any force to the left is negative. So when I add the forces together, I have 12 newtons plus a negative 8 newtons, and I'm still going to divide that by the 2 kilograms of mass. Now, 12 minus 8 is 4 newtons divided by 2, and we're going to have 4 divided by 2 is 2 meters per second of acceleration. It's still to the right, came out positive, and the majority of the force is to the right. So again, those are all vector quantities. Direction does matter, so be careful with your directions. If we get into a situation where our forces, our applied force is not straight across, then we're going to end up trying to make it do so. So we're going to break it down to components. So a quick reminder of breaking something into its 2 components. If I have a force of 13 newtons at an angle of 23 degrees, to determine its x component, that's the adjacent side of that right triangle, so I'm going to multiply the cosine of the angle times the hypotenuse. In this case, I'm going to multiply 13 newtons times the cosine of 23 degrees. And I get 11.966. I've got 2 digits there for significance, so that's going to round to 12 newtons. Okay, now whenever you're looking for the vertical force, in this case, it's on the opposite side of the triangle, so you're going to want to use Fy equals sine of theta times the hypotenuse. So with this situation, I want to use this 13, which is the overall force, I'm going to multiply that by the sine of 23 degrees. Now, 23 being less than 45, I should get less vertical force and more horizontal force, and I do. This rounds off to 5 newtons. So I've taken that 13 Newton force and I've turned it into a horizontal and a vertical component. That will allow me to line it up with frictional forces or other forces, and normal forces and gravitational forces. So that's one of the skills you're going to have to use over and over again as you move forward. So in the second case that I have here, same base idea, it's 52 newtons. I'm going to multiply that by the cosine of 40. So 52 times the cosine of 40. The other thing is to make sure you're in degree mode, because that is 40 degrees. So that's 39.8. Again, I have two figures, so that's going to be 40 when it rounds off. And then I'm going to take the sine of 52, the sine of 40, the angle, and make sure I close the parentheses there and multiply by the 52 newtons of force. I get 33.4. Two significant figures, that's going to round down to 33. So I have 33 newtons this way. Close to a 3, 4, 5 triangle. Essentially it is a 3, 4, 5 triangle. Just a little bit off. So one of the basic things you have to be able to do is break a force into its two component parts. That way we'll be able to get everything lined up so that you can easily and quickly cancel out whatever you can and add up the forces in the x and the y dimension to get an overall net force. Okay, so that's the first skill that you're going to have, and we're going to apply that to some situations as we go forward.